let's go ahead and get started.
Oh, what's the fun in that?
Yeah, I know. All right, if you remember from last class, we talked about actually how to build up to a transistors from the different physics up to creating diodes with p-type and n-type diodes, and we basically ended with how a transistor looks. So I'm going to go over this real quick, and then we're going to start talking about gates. How do you actually use transistors to make gates? And then we'll go into Verilog, which is the language we use to simulate basically gates in general. And then you actually can, with these gates, build a processor. Because remember, a processor is just really a bunch of these transistors etched on silicon connected via wires. That's all.
Simple.
It's simple. It is simple in one way.
Simple for
completely confusing in another. All right. So again, a transistor. You look on the left. This is, I guess, the standard way they're built. If you remember, the p-type silicon has holes in it. Yes.
Her power just went up.
Oh, okay.
Percent. Instead of down.
Basically, has holes where it's essentially pulling the electrons, so to speak. Again, I'm waving my hands here, waving, because we're not EE majors. And N-type has basically free electrons that can be pushed around.
Magic.
Wow, it's magic. So if you apply voltage to the gate, which is essentially pushing electrons in that way down, it allows you to connect from the source to the drain because you have free electrons between the two. If you don't apply the gate, then the drain is basically being sucked into the p-type silicon and creates high resistance. The thing to keep in mind is it's not a full connection or a full stop. It's really low resistance and high resistance. It's just low enough to be a connection or high enough to be not a connection. Okay. Now that we've talked about that, I will hopefully stop waving my hands. Here's a nice, beautiful 90s graphic.
Yeah.
Yeah.
It's gorgeous.
It is gorgeous, isn't it? All right. So when we start going into computer science, we think a little bit higher with inverter. What was that all about, Matt? Come on, out with it. Do you just not like the table? Is that it?
Well, I'm dealing with truth tables right now, so I'm.
Oh, really?
Oh, yeah.
Ooh, which class is doing truth tables?
Discrete.
Oh, okay. Well,
So
luckily we are using truth tables here, but they're going to be pretty simple.
Yay.
So an inverter, it basically takes what you have and invert it. So if it's zero, I know. Thank God. I know.
Good
So
thing
if
they
it's
made
zero
this.
or low voltage, it'll create a 1 or high voltage. If it's high voltage or a 1, it creates a low. Is anyone confused? Yes.
No.
Oh, okay, good.
Can you say it one more time?
That's why we recorded
Thanks.
this.
All right, the symbol we use is basically this triangle with a little circle around it. In reality, this circle around it is all that matters because that's what's saying not. All right.
Don't do this.
Any questions? So here's our symbol. Great. Oh yeah, how can we build one with transistors?
Picture.
With a picture.
I like pictures. With the gate.
With a gate.
Oh, that was actually there too.
Let me at least do this first one for you.
I like the fact that the.
All right. So remember, you have I, your input. That's going to be plugged to the switch, and then you have your output here. So the idea is that when you apply input here, it's going to connect to ground, which means that your voltage will be connecting to ground and actually lowering the voltage going this way because there's a high connection in this direction. Remember, electricity wants to take the easiest path. Keep in mind that you're applying voltage over here. That's how you actually create the high current. In case you are not connected, then you have a voltage just being applied to make a high voltage. If you are applying current here, then the voltage being applied over here will basically be connected and go back to ground, which will make it low voltage or zero. Okay, you got it?
Sure.
All right, great.
Electricity.
Any of y'all done these breadboards before?
No.
Oh, no one's done breadboards?
It's called a breadboard.
You got one? Or no?
Why is it a breadboard?
Is it made of?
Well, it's got, yeah, I don't know.
Head.
I don't know where I was going with that. The thing about breadboards is all these columns are all connected, but they're not connected via rows. So, for example, this pin right here connects to this wire up here, which you can then connect. Yeah.
Okay.
So this guy right here, hopefully you've seen a resistor before, connects to, looks like this pin up here and goes over here, and that's a light. So you can have little flashy lights. If we were going to digital logics, we'd make like a little adder so we could put something on and then watch the lights change, and then you'd have addition happen.
This makes me think of Minecraft with all the little.
Yeah, yeah, exactly. Except it'd be reality.
Yeah. Except it's real.
It's actually real, as opposed to
You can
Minecraft.
actually build stuff.
You would actually. Yeah.
I mean, you can build stuff virtually there. So
the standard resistor, this over here, packaging, it could have been a processor. You can also just put different gates inside of it. It's really just packaging for whatever you need, and then it has little feet that connect back into a breadboard. Okay. Awesome. All right, the first thing, NANDs, which is negated and. Sometimes I will call it not and,
it looks like a plug.
but it's really negated and. It looks like, well, kind of. Remember, there's a circle, which means not.
A plug with a bead on it.
All right, there we go.
Sure.
I for some reason, my brain thinks round bullet.
Round bullet. It looks like God, what are they from Mario?
Yeah, the little bullets that come out. Exactly, from Mario. Except it has a little circle in front of it, so it's a NAND.
He's pushing it.
All right, truth table. So it has two inputs, A and B. What's the AND of 0 and 0? Right, or 0, and when you not that, it becomes 1.
High
1,
voltage.
right, you do, yes. You said you had a question?
No,
Oh, I
it's
thought you
high
said
voltage.
Okay.
I'm saying the answer.
So AND of 0 and 1, just going to go through these. And the AND of 0 and 1? If you're wrong, then it's obviously the other choice, right? 0. And then when you not 0, you get 1. Oh, this is doing great. 1 and 0?
1.
Hold
0.
on. Don't take guesses.
Well, I mean, it's up there.
50-50.
No. The AND of is 1 and 0 is 0.
Zero.
And then when you not it, it becomes 1.
That's what I said.
All right.
Why is the end of 1 and 0?
The AND of 1
Because
is
there's a 0.
because there's a 0.
Oh, okay.
Multiply by 0.
Yeah, sure, multiply.
Sure, we'll go with that.
Yeah, multiply. I like that. 1 and 1, or 1 times 1 is 1, so when you not it, it becomes 0. Okay.
I was making the connection. I thought you were adding them, and I was like, 1 plus 0 is still 1. But okay.
Oh, I was going to ask, how do you do this? But I guess I automatically showed you.
Yay.
Woo!
Basically,
West?
the voltage will go through unless both A and B are connected. So this is how you build a NAND gate with transistors. By the way, all circuits can be built with NANDs. So all processors are really just one way to do it is a bunch of NANDs etched onto silicon. Call it a day.
Yay.
Okay?
Call it
Call
a
it a
day.
day.
Just call it a day, right? Yeah.
Can we call it a day now?
Yeah.
Nap time.
I'm kidding. I enjoy
Thanks.
this class.
So here's AND. What was the difference between AND and negated AND?
Negated ANDs makes it.
The picture,
not.
sorry, the picture.
Oh, the circle.
This circle, right. Now you just
Not
have,
pushing anything.
Now it's just the bullet thing.
right. So
Now it's just
AND
following the
of
line.
0 and 0, 0, 0 and 1 is 0, 1 and
That's the
0,
line.
0. Okay, 1, 1.
Not the
Are
back
these
is
truth
the
tables too bad? No?
Okay.
Okay.
Pretty straightforward.
I
Oh,
mean,
that's
If
good.
there's a 0, it's 0.
It's his line. He's
Now, your truth tables, did you have, how many choices do you have for every
Too many.
entry?
We're at 8 right now.
You have 8 right now? Okay, well, it's going to be simpler here since you have signals which are really low and high, which you would think would only give you 2 options, but actually give you 4. But we'll give you to that. We'll get to that in a moment. Okay.
Whoa.
Whoa! Or gate.
Oh
Or
no. This is
gate.
where it gets.
It's like an arrowhead to me.
Yeah. Or
If
the
there
jet
is a
settings.
1, if there is a high voltage, it will be high voltage.
Right.
Okay.
Ta-da!
Yeah, or once is trying to become 1 and just trying to become 0.
Yeah, and it's like you have to have 2 of the same thing for it to be
Right.
1.
Yeah.
This is
All right,
Oh,
and
no.
here,
There's a,
What the?
it's an XOR. Oh, please tell me you
Sure.
have seen XOR before.
No, it sounds like a Pokemon now.
Yeah,
It
The
really does.
the XOR.
XOR.
I'm pretty sure there is a
For some
Pokemon.
reason I thought of like Onyx and stuff.
So what is XOR? What is it doing?
XOR. Going in an X.
It's like
Metacross?
It's going in an X?
So like
It should be XOR.
the OR of 0 and 1, looking at A and B.
Right. But what about 1 and 1? That goes to 0. So what this is called, it actually does exist. It's called exclusive OR, meaning that it's one or the other, but it can only be one because
This
it's
is the
exclusive.
thing that we said we weren't going to do on the screen.
Or is actually called inclusive OR because if both of them are true, it's including both of them. Exclusive means it can only be one, and that's what the X is. So in English, which one's being used?
The 1?
The
No,
zero.
the 0.
Hold on. In English, does English use XOR or OR? This is actually really tricky.
XOR.
It does use XOR technically. And that's why we get confused in
One and
computer
only
science
one.
all the time because I always think of this when someone says OR. I'm like, yeah, of course, sounds great. Oh, wait, I'm sorry, you didn't mean both. So yeah, a little tricky. Sorry about that, guys. That's how it is. But yeah, XOR.
Makes sense. XOR to get one has to have one each.
Yep.
5%.
All right, so if you have two inputs, if you have two inputs, each of which can have two values, how many truth tables, two inputs with one output, how many total possible truth tables can you have? In other words, truth tables that look like this. You have two inputs, one output, and you have 4 columns. How many total possible truth tables can exist? Well, here's the first 8.
Okay.
See, the first 2 columns are always the same. We're just changing what the last output column is. And we put the 1 up there, 1 right there. Put the 1 here, 2 zeros, 1 0 1 1.
Yeah, this really is discrete math.
See, now you know why we make you take that course. That and data structures hopefully shows why.
Yeah, but it's a good different data structures.
Oh, nice.
Take it
And
now.
linear.
All right, so how many total truth tables do you think there are?
8. 1 to 8.
These are the first 8.
There's
Oh, no. there's
16.
more.
Yeah, there's about 16 here.
There's oh no, there's more. Yes, there's more. What gave it away?
Okay. So with 2 inputs and 1 output, there's only 16 possible truth tables or circuits, so to speak, that you can create. That's just a side comment more than anything.
Yay.
All right. How are we doing here? Oh, any questions so far about the gates? Nap time? All right. So we have talked about quantum level conductors, doping, building, and we just talked about building gates. So I'm going to go ahead and pause the video, and before we talk about common, actually we're going to stop here and go talk about Verilog because I think we're ready for it. Yeah.
So we can do our lab.
Yeah. So you can,